In the darkness between the stars, something vast is moving toward us. Astronomers call it Three-Eye Atlas, the designation's eye marking only the third confirmed interstellar visitor in human history. Unlike the smaller fragments seen before, this candidate appears immense. If its surface is dark, current estimates imply a diameter approaching 20 kilometers, a scale that dwarfs anything else ever observed crossing into our system. Yet, its brightness raises questions. It shines more intensely than expected from such a body, especially when compared to predictions from standard rocky or icy models. What test, then, could distinguish stone from signal? The first traces of Three-Eye Atlas appeared in late June, not as a sudden spectacle in the sky, but as faint imprints hidden inside routine survey images. These images were gathered by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a pair of wide-field telescopes stationed in Hawaii. Built to scan for subtle patterns of motion across dense star fields, the system flagged an anomaly so faint it nearly dissolved into noise. Astronomers repeated the data checks, subtracting frames, filtering out cosmic rays, and confirming the tiny thread of light that persisted from one night to the next. After careful reprocessing, what looked at first like a statistical artifact revealed itself as an actual body. The object did not announce itself with drama, yet that very quietness became the setting for one of the most consequential detections of recent years. Survey instruments catalog countless moving points each night. Most conform to well-known families, asteroids looping on closed ellipses, comets tracing elongated arcs under the influence of solar heating. This new trace behaved differently. When its positions were plotted, the orbit refused to curve back into a bound path. Instead, the trajectory stretched open on a hyperbolic line. Such a shape indicated that it was not captured by the sun's gravity. In other words, the calculation showed it was not of our system at all, but passing through from interstellar space. Its relative speed only reinforced the picture. Current trajectory data place it at well over 150,000 miles per hour with respect to the sun, swift enough to escape completely once its flyby is done. That recognition sparked a troubling question. If this visitor measured close to 20 kilometers across, an order of magnitude larger than either of the two earlier interstellar detections, how had it gone unseen until now? By rights, an object with so vast a surface area reflecting sunlight should have been conspicuous months before. Yet there it was, captured almost by chance, appearing at the edge of perception, as if it had been hiding in plain sight. Was its surface so dark that it only brightened after shedding material, or have our methods still been too blunt to recognize such signals until they press against our doorstep? Brightness became the puzzle's heart. In astronomy, size estimates often rely on brightness. How much light an object reflects depends not just on its diameter, but on the albedo, the fraction of incident sunlight scattered back to space. If an object's surface is dark, calculations inflate the size to explain its luminosity. If the surface is shiny, the same light can be generated by something smaller. In this case, the reported brightness was too strong for typical dark rock or carbon-rich dust. To match the observations under those assumptions, the body would need to stretch toward that imposing 20-kilometer scale. If instead the surface was laced with fresh ice or crystalline frost, its true bulk could be less. The contradiction sat unresolved, but either way, the interloper turned out to be larger and brighter than anticipated. Comparisons to mirrors were sometimes invoked, not literally, but as shorthand for how unusually reflective it appeared against expectation. The known catalog of asteroids and comets supplied few close analogies. Something about its surface or its interaction with sunlight was skewing the familiar rules. That ambiguity deepened its sense of strangeness. A body massive enough to scatter plenty of radiation and luminous enough to demand an explanation other than standard rock or dust. Too large to slip by unseen, too shiny to conform to simple models. The paradox hung heavily over the data. In the end, the formal designation Three-Eye Atlas became a placeholder, a marker for something that blurred categories. Each frame of survey imagery added to the contradiction rather than resolved it, reinforcing the impression of an object that challenges familiar expectations for visitors from deep space. And this invites another question. If we now count it as the third confirmed interstellar body, what does it mean to be the third? How do the echoes of earlier encounters help us interpret an arrival of this magnitude? And what patterns emerge when we place them side by side? Each time a new interstellar visitor is logged, it inevitably recalls the ones that came before. The name 3I Atlas immediately draws a line back to 1I Oumuamua in 2017 and 2I Borisov in 2019. Two discoveries that shattered the idea of our solar system as a solitary enclave. To grasp the weight of Atlas's presence, it helps to revisit those first encounters and the contrasts they etched into our expectations. The story begins in October 2017 when Oumuamua streaked through inner space. Its Hawaiian name, meaning scout or messenger, captured the sense of something arriving unannounced from elsewhere. What astonished researchers was its geometry and motion. The light curve brightened and dimmed with a rhythm suggesting an elongated body, perhaps cigar-shaped or even pancake-like, tumbling as it went. More puzzling was the acceleration. As it moved away from the sun, its speed increased slightly, as though nudged by a force beyond gravity. Normally, this is explained by jets of vaporized ice venting from a comet's surface, but Oumuamua showed no coma, no tail, no visible outgassing of any kind. Without those usual signatures, the cause of its extra push remained a mystery. Even today, the question lingers as an unsolved problem, a body not acting like the asteroids or comets we thought we understood. 2 years later, in August 2019, another voice joined the chorus. Amateur astronomer Borisov spotted a new interloper, and when its trajectory was calculated, it became designated 2I Borisov. Unlike its predecessor, this visitor did display a sunlit coma and a trailing tail, fitting neatly with the behavior of active comets. But once spectroscopic analysis came in, the details complicated the picture. The detected chemistry spoke of conditions colder and more extreme than our own early solar nebula. High levels of carbon monoxide hinted at formation far from any star's warmth, deep in the icy outer disk of a different system. So even though it looked familiar, its composition carried a whisper of alien origins, evidence of planetary nurseries distinct from our own. Then arrives 3I Atlas, and the sequence feels less like an oddity and more like a pattern unfolding. Where Oumuamua was small, confounding in its dynamics, and Borisov more conventional, though chemically distinct, Atlas pushes the scale into uncharted territory. If Oumuamua could be likened to a mountain, and Borisov comparable to a typical cometary nucleus, then Atlas, at nearly 20 kilometers across, is closer in scale to a city or even a small island. The disparity is stark. Side by side in a diagram, the third column towers above the first two, like a wall against the horizon. But timing is as striking as scale. Humanity scanned the skies fruitlessly for centuries, yet since 2017, we have logged 3 of these passers-by in rapid succession. What explains the clustering? Perhaps interstellar fragments have always slipped quietly past, unnoticed in the background. Only with automated sky surveys like Atlas have we gained the sensitivity to spot them. And the next leap in this capability looms with the Vera Rubin Observatory, now in its commissioning phase, which will scan the entire visible sky every few nights. Its field of view could reveal not just a handful, but perhaps dozens of interstellar objects within the coming decade. That context matters. What feels sudden may partly reflect our improving tools. Yet it is also possible that the solar system now drifts through a busier region of the galaxy, a place stirred by stellar tides that send debris scattering across interstellar space. The implications ripple outward. One messenger with unaccountable acceleration, a second with a chemical fingerprint distinct from anything near the sun. And now, a third, massive beyond precedent, luminous in ways that do not fit easily into models of rock or ice. A single anomaly might be dismissed as chance, 2 as coincidence, but 3, within a few years, hints at a hidden structure, a rhythm in the flow of objects across the galaxy. The questions grow heavier. Are these wanderers scouts of chaos, fragments shaken free from alien systems, or signs that the void between stars is far more crowded than we dared assume? If three such different visitors appear within so brief a span, which story do the data actually tell? And that leads us to the crux of the current enigma. For at the heart of 3, I-Atlas lies not just its size or brightness, but a deeper conflict still unresolved. A debate over whether this immense body is simply stone and ice, or if the signal it carries is something more. The discussion now turns to one of the most divided questions surrounding 3I Atlas. Is its brilliance and scale evidence of a natural body, or could it carry a signature of design? Known in shorthand as the debate between stone and signal, this tension arises not from idle speculation, but from measurable features that resist easy categorization. The light it reflects stretches the limits of natural explanation, yet leaping directly to artificiality strains scientific caution. Somewhere between those poles lies the debate that now surrounds the object. For most astronomers, the working assumption remains conservative. Atlas is best explained as a natural body. One of the strongest arguments is that highly reflective ices could still cloak its surface. When comets enter warmer regions, solar heating can lift away dusty crusts and expose clean crystalline ice beneath. Such fresh exposures scatter sunlight with unusual efficiency, making them appear brighter than expected for their size. If Atlas fractured or shed layers on its way inward, entire swaths of reflective terrain might have been revealed at once. Under this model, its glow becomes consistent with known phenomena without invoking anything more exotic than resurfacing ice. But even this natural picture presents difficulties. Based on its observed brightness, if its albedo is moderate rather than extreme, the size required climbs toward 20 kilometers wide. No interstellar visitor detected so far has come close to such a mass. In our own system, planetesimals that reach those dimensions are relatively fragile and prone to break apart over time, and the odds of one surviving an ejection across light years to appear intact here are slim. It is not impossible, but the scenario stretches assumptions to their limit. Rising on the other side of the conversation is Avi Loeb of Harvard, who urges against closing the door to alternatives. He emphasizes that openness does not mean leaping to conclusions. It means proposing observational tests that could sharpen the evidence. His suggestion is to use the James Webb Space Telescope to monitor the body with extreme precision, tracking its trajectory, actually over weeks or months. The goal is to look for subtle deviations from purely gravitational motion. Tiny non-gravitational accelerations that could signal outgassing or, in the more radical hypothesis, directed propulsion. This is not without precedent. In cometary physics, non-gravitational acceleration is well understood. When gases vent into space, they act like miniature thrusters, producing a measurable nudge. The push is always tied to a visible coma or tail. But Oumuamua in 2017 complicated that picture, showing acceleration without a detectable plume. That anomaly remains unresolved, and Atlas now presents a chance to examine whether similar forces operate. By monitoring with Webb, astronomers could rule out or confirm whether ice sublimation explains its path. If no venting is visible but acceleration persists, then natural explanations may begin to narrow. Even so, most of the scientific community cautions restraint. The prevailing stance is that reflective ices and unseen outgassing still provide the likeliest explanation, and that extraordinary claims require extraordinary evidence. Current data consist of brightness measurements, orbit determinations, and light curves. Interpretive, incomplete, and in need of higher fidelity before any decisive claims can be made. For this reason, the mainstream view anchors to what is most probable: dust, ice, and rock carried here by chance. And yet, the unease does not fade. If evidence eventually showed sustained, unexplained accelerations without a corresponding coma, scientists would be pressed to consider mechanisms beyond ordinary physics. In that case only, the door would open wider to exotic interpretations, which could include artificial origins. Such reflections are framed not as conclusions, but as contingencies. Paths of thought dependent on what future data reveal, not proclamations of present fact. The debate then is not simply about classification, but about how science positions itself between evidence and possibility. A natural explanation offers continuity with all we know of comets and planetesimals. An artificial explanation would redefine our relationship to the galaxy. The two options sit on the same spectrum of investigation, divided not by ideology but by thresholds of evidence. The result is a kind of mirror, forcing those who study the object to confront their own balance between skepticism and curiosity. Astronomers can model trajectories, measure brightness, and point telescopes, but in the gap between natural probability and speculative wonder lies a more personal reflection. What we see in this visitor is shaped not just by its surface of ice or stone, but by the questions we are willing to ask of it. And it is here that we approach the final point: how Atlas, massive and enigmatic, reflects back something not only about space, but about ourselves. What can we say with certainty about 3I Atlas? We know it is interstellar, we know it is immense under standard brightness assumptions, and we know it reflects more sunlight than expected. What remains unsettled is the cause of that reflection, whether it is ice, fractured rock, or something stranger. We also do not yet know if its flight path hides any tiny accelerations, natural or otherwise. What decides the question will be observation, precision tracking with the James Webb Space Telescope, surveys with Vera Rubin, and the patient accumulation of data. Given the evidence so far, which explanation convinces you? Giant reflective ice, a rare fragment, or something else? If you found this exploration useful, subscribe and share your view in the comments.